Now, in this section, we're going to continue talking about statistical studies, but now talking about the different types of statistical studies and how they are constructed, what do they mean, and what are the different situations we use them for. So, in a statistical study, we have things called subjects. The subjects of the study are the people, animals, or other living things or objects chosen for the sample. If the subjects are people, we might refer to them as participants rather than subjects of the study. And then the first kind of study is called an observational study. In an observational study, researchers observe or measure characteristics of the subjects, but do not attempt to influence or modify these characteristics. So like the Nielsen example of, surveying for who watches the Super Bowl, it's strictly observational. They observe how many watch, or they try to survey for how many who watch, but they don't influence that number. In an experiment, however, researchers apply some type of treatment and observe its effects on the subjects of the experiment. So we're administering something like a drug or a medicine and attempting to influence some type of change as a result. And then we observe the results. And so here's a case study. In 1954, a large experiment was conducted to test the effectiveness of a new polio vaccine created by Dr. Jonas Salk. It involved a sample of 400,000 children chosen from the population of all children in the United States. Half received an injection of the Salk vaccine. The other half received an injection that contained a harmless salt water injection. Among those who received the vaccine, only 33 contracted polio. However, there were 155 cases of polio among those who did not get the vaccine. And so, using the techniques of statistical science, which is something we'll get more in detail about later, the researchers concluded that the vaccine was effective at preventing polio. So, what kind of study was that? Was it observational or experimental? So of these two situations here, we're going to identify an observation versus experimental study. The Salk polio vaccine study had a treatment, so it's going to be what we call an experimental study. They were testing a treatment, in this case the vaccine. On the other hand, a poll in which college students are asked if they commute or live on campus would be considered observational because it does not attempt to influence outcomes, but just determine behaviors by asking questions. So that's the big difference here, experimental versus observational. Experimental, there's something done or given in order to try to cause a change, whereas observational, merely observing, asking questions, and recording the results, but not trying to influence any change. And so a few other definitions here. A variable is any item or quantity that can vary or take on different values. The variables of interest in a statistical study are the items or quantities that study seeks to measure. When cause and effect may be involved, an explanatory variable is a variable that may explain or cause the effect, where a response variable is a variable that responds or changes in the explanatory variable or due to the explanatory variable. So here what we're going to do is identify the variables of interest in each of these studies. Starting with that polio vaccine study, there are basically two variables here, the vaccine and polio. Vaccine, you could either have it or not get it, or polio, either did or did not contract. And so we would refer to the vaccine as the explanatory variable, since it might explain why somebody does not contract polio, whereas the polio would be considered the response variable because it could respond to whether or not the treatment was received. In this next one, however, we could say that this poll in which college students are asked if they commute or live on campus, that was an observational study. And its variables are simply going to be the responses to the questions which were asked. For instance, how do they commute? There's no explanatory or response variable in an observational study, like there are for the vaccine, where we have a treatment and so forth. So some variations on observational studies. The most familiar observational studies are those in which data are collected all at once, or as close to that as possible. Two variations on observational studies are also common. A retrospective or case control study uses data from the past, such as official records or past interviews. A prospective or longitudinal study is set up to collect data in the future from groups that share common factors. So basically, we kind of have the situation where a study could be done in the present, or it could look back, retrospective, to past data, or it could be set up to collect data in the future as groups continue to do different things, and so we just continue to collect data throughout the years. So we're going to talk about a few different cases. Which kind of study should we use? So here it says you want to know whether teens who try marijuana are more or less likely to abuse hard drugs as adults. What type of study would be appropriate? Experimental or observational? Retrospective or prospective? Well, in this case, an observational retrospective study would be the most appropriate because it would be unethical and really illegal to perform an experimental study where we actually were to use the drug and then observe things after that. So we have to perform a strictly observational study. Looking at past experiences, so it would be retrospective. That's really our only option here. Another thing is, suppose you want to study if vitamin C has an effect on colds. Suppose people taking vitamin C daily get an average of 1.5 colds in a 3-month period. How can we know if this is really an improvement or not? It might seem like it's a pretty good number, but do we know if that's a really good, just have an average of 1.5 colds, or if that's actually not good at all? Well, that's where we have to have different groups for testing. So some people have to take vitamin C and some do not during the study. And so this would give rise to the treatment and control groups, which are usually randomly assigned. So the treatment group is an experiment is the group of subjects who receive the treatment being tested. And the control group in an experiment is the group of subjects who do not receive the treatment being tested. So this gives us a way of comparing, does a particular treatment, like say vitamin C, make a difference? Well, now we can compare it with the control group who did not get it, and we can see did it actually make a difference or not. Looking again back at the Salk polio vaccine study, we already kind of mentioned what the treatment is here, but which group of children constituted the treatment group and which constituted the control group? Well, the treatment was the vaccine, because that's what was given in order to try to see if it made a difference. The treatment group received the vaccine, received the treatment. The control group were the ones that received the injection of salt water, which was just a harmless thing that really shouldn't make any difference. So that would be the treatment group and the control group. So the control group didn't actually receive the vaccine, So we could tell, did the vaccine make a difference versus the control group? And so here's another situation. It says a study divided students into two groups. One group listened to Mozart or other classical music before being assigned a specific task, and the other group simply was assigned the task without listening to music. Researchers found that those listening to the classical music performed the task slightly better, but only if they did the task within a few minutes of listening to the music. The two groups performed equally on tasks given later. So in this situation, what is the treatment and control groups? The treatment was the classical music itself. This is what, again, was given to one group in order to see if it made a difference. And the treatment group were the group that received the treatment who listened to music. The control group were those who did not listen to music. And so now as a result, we can say, okay, the treatment group, how did they compare having listened to music with the control group who did not? And so that's why we need to have these two groups again so we can make that comparison. So using control groups helps again to account for unknown variables. However, it's not exactly perfect all the time, because what if other variables are influencing things that are still not taken into account? For instance, consider a study where a teacher seeks to determine if students working collaboratively work better. The teacher chooses 5 students who will study collaboratively, that'll be the treatment group, and 5 who do not study collaboratively, that'll be the control group. The teacher chooses students who have a high grade point average and are known to work diligently. So this was done to try to take any variation out of play for how much they would actually work. And so the study found that the students who worked collaboratively did better. However, the study found this information, but unbeknownst to the teacher, the collaborative students were in a dorm with a curfew, which ensured that they slept more regularly. So there was an extra variable. There was what we call a confounding variable, the amount of sleep, which was not taken into account, which could have actually skewed the results one way or the other. So the sleep could have actually been the deciding factor in who did better and who did not, versus working collaboratively. So we use confounding to say when this situation occurs. So a study suffers from confounding if the effects of different variables are mixed, so we cannot determine the specific effects of the variables of interest. The variables that lead to the confusion are called the confounding variables. If the treatment and control groups can differ in important ways, confounding can also result. And so researchers try to overcome this in 2 ways. 1, by selecting groups at random, or 2, using sufficiently large groups. So by selecting groups at random, we make sure that the subjects of the experiment are assigned to the treatment or control groups at random, meaning that each subject has an equal chance of being assigned to either group, or not tending to favor one over the other. Using sufficiently large groups, this makes sure that the treatment and control groups are both sufficiently large and that they're unlikely to differ in a significant way, aside from the fact that one gets the treatment and the other does not. We want that really to be the only factor that differs the two groups, if at all possible. So when an experiment involves people, more effects can occur simply because people know they're part of an experiment. This effect is called a placebo effect, and the detrimental effects of it on the statistical results can be lessened by the use of a placebo. So a placebo lacks the active ingredients of a treatment being tested in a study but looks or feels like the treatment so that the participants do not know whether they are receiving the placebo or the real treatment. The placebo effect refers to the situation in which patients improve simply because they believe they are receiving a useful treatment. So, for example, in the Salk polio vaccine experiment, the use of a placebo, the saltwater injection, was used to eliminate the possibility of the placebo effect. Eliminate the possibility that just because people thought they were receiving something, they acted differently in some way that could influence the results. So sometimes the knowledge of also the experimenter as to who or who does not have the placebo causes the experimenter effect, a type of confounding. For example, a researcher might unknowingly act different when interviewing a subject. And this behavior can actually cause the subject to answer differently as a result. So another variable we want to eliminate from our statistical study if at all possible. And so we say that an experimenter effect occurs when a researcher or experimenter somehow influences subjects through such factors as facial expression, tone of voice, or attitude. And so there's an experimenter effect was sometimes referred to as the Rosenthal effect after Dr. Robert Rosenthal. He came up with a situation to highlight this. And so in one example, what he did was he told a group of graduate students to study the performance of different groups of rats at certain tasks. He explained to the graduate students that one group was smarter and should perform better as a result. And after performing the experiments, these students actually determined what he said was true. However, he did not tell them the real situation, which was the selection of the rats were strictly at random. There was actually no, quote, smarter group. So what happened was his mental suggestion influenced how the students interpreted, recorded, or otherwise reported the results that they found. So the experimenter effect can happen when the mental suggestion influences how the study is conducted. So we want to remove that from happening in any statistical study, obviously. So in order to overcome the experimenter effect, a technique called blinding is used. So we have something called a single blind study. And in a single blind study, participants do not know whether they are members of the treatment group or the control group, but the people who are observing them do know, the experimenters do know. However, in a double blind study, neither the participants nor any experimenters know who belongs to the treatment group and who belongs to the control group. So everybody is blind to the fact of, who is in which group. And so that would eliminate any possibility of either the participants being influenced or the experimenters being influenced by knowing who is in the treatment or control groups. So to highlight these ideas, for each of these experiments, we're going to identify any problems and explain how the problems could have been avoided. So first off, a new drug for ADHD is being tested for its effectiveness. How they did this was they randomly selected children with ADHD, divided them into treatment and control groups. They used single blinding, which means the children in the treatment and control groups did not know which group they were a part of. And so experimenters evaluated the children's behavior during one-on-one interviews. But because it was single-blinded, the experimenters did know when a child was in the treatment group or the control group when they interviewed them. So could that have been a problem? Indeed, interviewers might have actually inadvertently speak differently or interpret behavior differently because they know which subject received the actual drug and who did not, the treatment and control groups. And so the experimenter effects could actually confound the results because the experimenters could be influenced by what they know. So this one probably should be double-blind as a result, so that neither the participants nor the experimenters know who's getting the treatment and who is not. Here's another situation. It says researchers wonder whether drinking coffee before an exam improves performance. And so what they did was 50 coffee drinkers are told not to drink coffee in the 4 hours before an exam, and 50 non-coffee drinkers are asked to drink at least 2 cups of coffee in the 4 hours before an exam. Both groups had the same average performance on the exam. But is there anything not quite right with the way this is set up? Indeed, the issue here is both groups took the exam under conditions which were unnatural for them. Even though we have a treatment and control group, one who drink coffee and another group who does not, they kind of mixed it up in a weird way. Coffee drinkers were deprived of coffee, and non-coffee drinkers were forced to drink it. That caused a situation which was totally unnatural for them. So perhaps a better way to do this is random sampling or something other than trying to mix it up this way, because this is creating unnatural conditions for the participants. Another example here says researchers wonder if the effects of a rare degenerative disease can be slowed by exercise. So they identify 6 people suffering from the disease and randomly assign them to 3 to a treatment group that exercises every day, and 3 to a control group which avoids exercise. After 6 months, they compare the amounts of degeneration in each group. We've got the control group, we've got the treatment group, so at least we have that much. But is there any, again, issue here with how this is set up? One of the issues is results will be difficult to interpret because there were only 6, and the sample size is really not sufficiently large. Another possibility to look out for is kind of like the coffee drinking. If those who exercise are asked not to, something that's not normal for them, it may create other health problems that could confound the results. Another situation here says a chiropractor performed adjustments on 25 patients with back pain. Afterwards, 18 of the patients said they felt better. He concludes that the adjustments are an effective treatment. In this statistical study, notice that there's no treatment and control groups here. The 25 patients who received adjustments represent a treatment group, but there's no control group. So we don't have the 2 groups. So the patients might also be just feeling better because of the placebo effect rather than any actual effects of the adjustments. So a situation like this should really be, well, we need the control group and we need the treatment group, and probably also needs to be blinded as well, so to try to reduce the placebo effect. And so to wrap up this section, what we're going to answer is, for each of the following, what type of statistical study is most likely to lead to an answer? So if you'd like to think about them for the second, you may want to pause the video here, and then I'll go through them one by one. In the first case, what is the average mean income of stockbrokers? An observational study would be the best thing to do here, since we're not really doing an experiment by giving a treatment, we're just observing and recording the average income of stockbrokers. So a survey, an observational survey. Do seatbelts save lives? Not really a situation where we should run an experiment, because that's not very ethical to ask people to not wear a seatbelt just so that we can check whether it works. So a retrospective observational study would be appropriate here, looking back on past data where people did or did not wear seatbelts, and strictly observational. So in the next one, it says, can lifting weights improve runners' times in the 10K race? This would be a situation for an experimental study where we have a treatment group which lifts weights and a control group which does not. There's no real way of doing blinding here because everybody's going to know, who's lifting weights and who's not. The participants certainly will. So experimental and no blinding is really necessary there. Now the next one, it says, does skin contact with a particular glue cause a rash? This is another situation where we could do an experimental study where one group receives contact with the glue and one does not. Blinding is not necessarily required unless we're worried that people will interpret things as a rash when that's really not. But single blinding is possible, where we could use something that looks like the glue but isn't really the glue for the control group. So the treatment group would get the real thing, control group would get something that looks like it but doesn't actually contain the glue part of it that might cause the rash. The placebo is what we would call that. And so the next one says, can a new herbal remedy reduce the severity of colds? This is one where an experimental study certainly would be appropriate with double blinding and a placebo, because the treatment group would get the remedy, the control group would get something that looks like the remedy but doesn't actually do anything. That would be the placebo. And so nobody would know who's in the treatment and control groups to eliminate the placebo effect and eliminate the experimenter effect as well. The last one here says, do supplements of resveratrol, an extract from red grapes, increase lifespan? This could be kind of done as a experiment, but we're dealing with a several year time span here. So we're going to use a prospective experimental setup where people use this extract, but we watch or record later on what their life expectancies are. Not really any need for blinding or anything like that, but it's perspective since it's going to be dealing with things that are going to happen well into the future. Now finally, they have something called meta-analysis, and this is where researchers review many past studies. So the meta-analysis considers these studies as a combined group with the aim of finding trends that were not evident in the individual studies.